Okay, welcome back to day 23 of Advent of Code 2022. We're getting near the end now. So, unstable diffusion. Oh, this looks like it has a nice input for a change. That doesn't fold into a cube or something. Or a multi-hole torus. The cube was the more complicated one, you wouldn't expect, but... Alright, you enter a large crater of grey dirt where the grove is supposed to be. All around you, plants you imagine were expected to be full of fruit are instead withered and broken. A large group of elves has formed in the middle of the grove. But this volcano has been dormant for months. Without ash, the fruit can't grow. You look up to see a massive snow-capped mountain towering above you. It's not like there are other active volcanoes here. We've looked everywhere. But our scanners show active magma flows. Clearly it's going somewhere. They finally notice you at the edge of the grove. Your pack almost overflowing from the random star fruit you've been collecting. Behind you, elephants and monkeys explore the grove, looking concerned. Then the elves recognize the ash cloud slowly spreading above your recent detour. Did you just... Before any of them can form a complete question, another elf speaks up. Okay, new plan. We have almost enough fruit already, and ash from the plume should spread here eventually. If we quickly plant new seedlings now, we could still make it to the extraction point, spread out. The elves each reach into their pack and pull out a tiny plant. The plants rely on important nutrients from the ash. They can't be planted too close together. There isn't enough time to let the elves figure out where to plant the seedlings themselves. You quickly scan the grove and note their positions. So the hash keys are the elves. Okay. Hello, DJ. So we've got a bunch of elves and a bunch of empty spaces, and apparently empty space continues in every direction, infinitely. Or I think that's the implication. Okay, so the elves follow a time-consuming process to figure out where they should each go. You can speed up this process considerably. The process consists of some number of rounds, during which elves alternate between considering where to move and actually moving. During the first half of each round, each elf considers the 8 positions adjacent to themselves. If no other elves are in one of those 8 positions, the elf does not do anything during this round. Otherwise, the elf looks in each of the 4 directions in the following order and proposes moving 1 step in the first valid direction. There is no elf in the north, northeast, or northwest. Okay, bunch of steps, and then they propose moving in these directions. After each elf has had a chance to propose a move, the second half of the round can begin. Simultaneously, each elf moves to their proposed destination tile. If they were the only elf to propose moving to that position. If 2 or more elves propose moving to the same position, none of those elves move. Okay. Finally, at the end of the round, first direction the elves considered is moved to the end of the list of directions. it's kind of a just complicated diffusion process. All right, fine. Right. The elves like to check up to round 10 that they're making good progress towards covering enough ground. Count the number of empty ground tiles contained by the smallest rectangle that contains every elf. Oh, okay. That's actually easy to compute. You just find the boundaries of the furthest elves. And take the width and height of that, times them together to get the area, and subtract the number of elves. Okay. Fine. Okay. Doesn't look that hard for part 1. Just need to do a lot of steps. Right. So this is our input. That's a lot of elves. Those are the hash keys of the elves. Alright, so like before, so I suggested a long time ago one of these problems that I will from now on use hash maps for these types of maps. Reason being, if you set a boundary, they can't go outside of that boundary. But hash maps you can kind of keep increasing depending on where they're going. Alright, so grid equals hash map. Okay, so all right. Now we need just extract the information. Let's say I line in, let's enumerate. Let's say grid if car is a hash, we just put that into the grid. So we go row column. Equals, it's an elf. What information do we need to record for this elf though? We're gonna have to record his oh, they don't each have an individual list of directions they choose. There's a global rotating list of directions they're choosing. I see. So actually, we don't actually need to store anything specific in the hash table. We can just store a boolean, or I don't know, just a 1. Okay, so we've got a grid. So the first, so we want to do 10 rounds. Okay, so 4 rounds in range 10. So in 1 round, we want to do 2 phases. Hang on. Is it 1 round they do nothing? Hang on, let me read this again. So, oh no, the round is split into halves. Okay. Okay. First half. Alright, so let me copy this in. We need to translate this into a table. Why does it paste it like that? Alright, just have to copy it in. So we need north, northeast. Okay, so we need directions equals. It's going to be a rotating list. So it will be a list of tuples. The first, yeah, tuples. The first bit will be the positions to check: north, northeast, northwest. But I want to do them as vectors. So it'll be north, so -1, 0. Northeast, -1, 1. Northwest, -1, -1. -1, 0. So this translates to saying, okay, it looks kind of ugly. Saying if there is no elf in these 3 directions, then we consider going this direction. All right. And then we just have to, I don't know, copy this, but with different numbers. 3, 4. All right, so the next one is south, southeast, southwest. So south, so it's just 1, south, southeast, southwest, and we end up going south. All right, it's easy enough. The next one is west, northwest, southwest. So west, so 1. Northwest is -1. -1. Southwest is 1 -1. Then we propose moving west. And finally east. East, northeast, southeast. East. Northeast. Southeast. East. Northeast. Southeast. And then we propose going east. There's a pattern here, so it could have been... Alright, anyway. That's the possible directions. So for the first half. So we go for elf position in grid. That will get us the keys, which is all we need. We check all adjacent positions, so we should really have a just a complete list of compass directions. So we got I could, whatever, we'll just write them all out. Help us understand. So start from, I don't know, west. That's not west, that's north. Fine, north. I don't want to go... Go clockwise, it's easier for my head to understand. East, southeast, south, southwest, west, north, west. Okay, that's all the compass directions. So if not any, get to use any for the first time in the advent. So we want elf position 0 plus compass position 0 just the same. I need to write a method for this. I'm probably going to be doing it often. Let's write this out first. If not any of these neighboring cells in grid or C in compass, so if there's no L's neighboring, we continue. Okay. Otherwise, we look through for it in range 4. We try 4 of the different directions, but starting from check directions, proposed direction equals directions so when it is 0, that will be it'll be, hang on, R% 4 plus it. Okay, so when R is 0, i.e. round 0, we'll actually start from the beginning, and it will increase 1, 2, 3. Okay. So we unpack the directions, so check directions and proposed direction. So we say we're gonna have to make we're gonna have to make a list of proposed directions. So let's say proposed directions equals a new table, because this way we look up the clashes. Unfortunately, it's time for the gym. We'll be back in like an hour if you're still slogging through this. I think it's likely. I mean, I could probably... This part 1 I'll probably finish before the hour, but part 2, you know how that normally goes. Alright, well, enjoy your workout. Check directions. So we want to say if not any we want D0, okay, D0 plus L position 1. So this is the position we're checking. Not any of these are in grid for D in check directions. Then propose directions of elf position will be grid is actually a set. Let's just stick with a set there. might be more efficient. So for elf positioning grid, blah, blah, blah. Proposed direction of this elf is going to be proposed direction, and then we break out of this for loop. And if we didn't find any, that's fine. We just don't do anything. We'll move on to the next elf. So if we get this far, or we will get this far, but we will have populated a set of proposed directions for a bunch of elves. Alright, now we have to create a proposed directions set equals set of values of this. So that means we'll actually look out for duplicates. No. No. That's not what I'm trying to do. I guess we want to use counter. Equals counter of proposed directions.values. So that'll just count how many times each one is hit. And now for elf position proposed direction in proposed directions.items. So we say if there's only one such elf trying to get to that position. No, not proposed direction. Proposed destination. Okay. We need to be clear on the difference here. Proposed destinations. Alright, so okay, if the counter records destination, just use the correct terminology here. If the counter is one and only one, then we move elf position there. So we do grid.remove elf position grid dot add proposed destination. All right. So that covers everything, right? At the end of the round, the first direction is moved to the end of the list of directions. So we go to the second one. Yeah, we've handled that. And finally, after round 10, count the number of empty ground tiles contained by the smallest rectangle that contains every elf. Okay. So now, min y, wait, let's min I, min j, min max I, max j, let's just say, just take some arbitrary elf. Elf equals set grid dot will that work? Can you do next on? No, you can't. Okay, you just do something like this for elf in grid. Min I, max I equals elf 0, elf 0, min j, max j equals elf 1, elf 1, and then immediately break out. So we just set them to sensible default values. Okay, now we do proper for elf in grid. Min I, max I equals the minimum of min I elf 0 and the maximum of max I elf 0. Just the same for the j's. Min I can be defined, whatever. Okay. So now we have the size of the rectangle. So height equals max I minus min I plus 1. Width equals max j minus min j plus 1. empty spaces equals, we just multiply them together, width times height, and then we're going to subtract the length of the number, basically the number of elves. Print okay. I'll just test this on the example. Let's try not to get wrong answers. Percent for, yeah, we need to do R plus IT percent for. Always do the modulus at the end. All right. Key error 40. So it's saying there is an ELF at 40. Remove elf position. So that elf position is in destinations. We added it from there. So elf position should have been in grid in the first place. What? So why would that fail? Also not second elf. Strange. So the only time we ever have anything in proposed destinations. Oh, we need to clean this every round, don't we? So it's been filling up with stuff. $99? No, it should be 110. So we're like 11 short. All right, fine. So we do 10 rounds, don't we? Although in this example they actually terminate Hang on, I don't think I've used the correct example. This example's not the same one. This is the example. Oh, that is the right one. Okay. Just having a look for... All right, let's... Okay. We're gonna have to print the grid. Okay, so we need... Oh, I'm not actually checking... No, I am. Okay, so... Let's make a method here. Define get grid from the grid. Basically, we do this. We take the min, the max. And then we do this. Oh, well, there's a bug. That should be 1. Could that be it? It would be nice to visualize this, but if I can solve it without doing so, okay. Then whatever's faster. Okay. I feel like this should just work then. I mean, it's not much complexity beyond that. 4146. Correct. It seems you're on the right track. Finish simulating the process and figure out where the elves need to go. How many rounds did you save them? The first round when no elf moved was round 20. Oh, bloody hell. Okay, so we need to basically do this infinitely. Num moved equals 1. While num moved. Okay, so round equals 0. So at the end of this, we say round plus equal 1. No. Don't use the word round. Okay, r equals 0 plus 1. While num moved. Okay, so num moved equals 0. Num moved plus equal 1. If we're lucky, this will just terminate on its own. What exactly did they want? They want the first round when no elf moved. So it would be, so we added 1 after that, so we have to subtract 1 again, so it'd be minus 1, but plus 1 again because they start from 1. So it'd be R. Alright, does this actually terminate? I need to print some stuff. Slowing down, so they're sort of reaching stability. 957. I mean, and I've not been showing my IDE. Apologies for that. Let me just quickly do that. Well, okay. Let's just paste this in. Correct. All right. I'll just show my code. So what I did was pretty straightforward. I just changed the for loop to a while loop, so it just goes on forever. We keep track of how many moved. As soon as they stop moving, we break out. We keep track of the round number, the number moved, increment the round at the end, increment num moved every time we move something. Those are the only things I had to change. And at the end, we print the round number as well as empty spaces. I'll just make this work for part 1 too. So if R is 10, break. I don't know. So if I were to do that, it should get me back to that. Yep. Was that the correct answer for the old one? 4146. Yes, okay. Alright, not the best way of doing it, but that was a very easy part 2 stemming from part 1. Like, you just run your part 1 program. That isn't normally the case for these. Well, at least it was for the first few days, but... See, this is reflected by a low number of people who only completed part 1 relative to completing both. There's no major complexity in this either. It's like... you just do the simulation. You don't have to figure out any clever way of finding a stable state or skipping steps or I don't know. The numbers are fine. Okay. Yeah. That's cool. So they were all solved within 25 minutes. I mean, for that problem, it kind of seems slow. I'm surprised. I thought people would be faster than 25 minutes in the top 100. Because it's very standard. There's no major trick to it. You just go through them all, check the directions, and there's loads of hacks for doing these compass direction stuff really fast, which I didn't use. I just wrote everything out explicitly, but you can make it faster. Cool. So how long did that take me? About 50 minutes. Pretty good. Alright, well, I guess DRJ, you won't catch me after you finish with the gym, because I finished pretty quickly. So tomorrow is day number 24, and then after that day number 25. I've heard they're supposed to be easy ones because Eric doesn't want to give us hard, difficult problems for Christmas Eve and Christmas Day. So that'll be nice. Nice cool down, and it'll give people time to catch up on all the ones they've missed as well. Especially like 16 and 19, which people are still struggling with. Well, let's have a look. Look at the... look at these. So we've got, 16, there's, no. 17, 19, 16, 17, 19, 18, 19, or, well, 16, 17, 19 are pretty low in terms of completion rate. And these two are recent, so... What was 16 again? This was the flow rate. This was where you actually had to use a smart dynamic programming paradigm. Some people probably don't know dynamic programming or don't remember it. Memorization, all that stuff. And the Tetris thing was kind of clever. Yeah, okay. Alright then, I'll see you tomorrow for Christmas Eve.